This is a digital printing overview with an introduction to inkjet printing. This presentation is supported by several readings, including the Helmut Kippen book, Handbook of Print Media, especially Chapter 5. Although this reading was not specifically assigned for the presentation, students may wish to refer to it for background information. Supplemental readings that were required, including the article by Heidi Tolliver-Nigro, Defining Our Terms, as well as the article by Finna entitled Digital Printing and Overview Part 1 from Flexo and Gravure Global Magazine, along with PIRA International report entitled The Future of Digital Printing Until 2018, and finally a couple of brief articles by Romano and Nelson from the 2005-2006 AGC Buyer's Guide entitled Variable Data and Buying Large Format Printing. With digital printing technologies, there are no permanent image masters as there are with conventional printing technologies. For example, with offset lithography, the process requires a printing plate, usually an aluminum plate, sometimes a plastic plate. With flexographic printing, the image master is also a plate, but it is a rubberized relief plate. And with gravure printing, the image master is an engraved cylinder. There are no such permanent image masters utilized with digital printing technologies. In the Handbook of Print Media, Kippen describes digital printing technologies as non-impact or NIP. To me, this is an unfortunate acronym as the word NIP normally refers to a nip point, which is common for impact printing technologies. So please do not be confused when referring to the Handbook of Print Media with this terminology. Whenever we talk about new or emerging technologies, it is important to think about what they enable. In other words, what the technologies mean to the incumbent technologies and workflows. In the sales world, sales professionals often talk about features and benefits. A feature is what the product has. The benefit is what it does for the user. For example, if someone is shopping for a lawnmower, they may have a choice between a 24-inch mower deck and a 36-inch mower deck. The feature is the size of the mower deck, while the benefit is the time that the larger mower deck saves the person who needs to cut the grass. So when we talk about digital printing technologies, and really any of the technologies that we talk about in this course, it is always important to keep in mind what those technologies are, as well as what they enable us to do. In the Defining Our Terms article, we are presented with a number of terms that surround digital printing. This article is rather dated. However, much of the information is still relevant today. It is important that we discern the nuances of these technologies so that we can fully understand the underlying concepts. The first term that's outlined in this article is the term digital press. A digital press is any device that has production capability and quality levels that would enable it to compete with a conventional printing press. Typically, these are differentiated from copiers insofar as the level of quality that they offer, as well as the production capability. The next term is direct-to-press. Typically, our industry uses this term to talk about direct-to-conventional press, much like the Presstech DI offset press that we saw at the Hub. In that demonstration, we saw direct-to technology, in that the digital information went directly to the press where the plates were imaged on the press itself. In a more conventional offset operation, the plates are imaged and frequently chemically processed separate from the printing press. Therefore, this particular configuration would not get the direct-to press tag. I suspect that one of the reasons why the term direct-to-press is normally limited to direct-to conventional printing technology configurations is that all digital presses are direct-to-press, whereas only a small minority of conventional presses support direct-to-press capability. The next term, short run, refers to run lengths that are economically handled by digital printing press configurations. They can be as short as one copy, and depending on the type of work, as many as several thousand, although normally it is defined as only up to a couple of hundred. The term on demand means the ability to produce what you want when you want it. Usually this is limited to digital printing technologies, which do not have the make-ready limitation of conventional printing technologies, so they make on-demand work possible. The next term, distributed printing, refers to a distribute and print model, which can be compared to a print and distribute model. This may be best thought of in terms of book printing. If a new Harry Potter book were to come out, the publisher would print several 100,000 or maybe even over 1 million copies that would be printed and bound and shipped to bookstores and department stores and airports and other retail venues all over the world because they know they're going to sell. This would be an example of a print and distribute model. Other books require more customized work. For example, some textbooks or course packs, which would be more effectively sold in a distribute and print model. The digital information can be available online, where the retailer or even the home user in some cases would output the book on demand or within a very short time frame from the order. For certain types of work, this makes great sense. The cost of shipping and inventory and the insurance to protect the printed inventory is very expensive. So when we talk about digital printing enabling things, the distribute and print model is one such capability. Variable data printing is really only economically feasible with digital printing. With variable data printing, some of the content is static, meaning it does not change, while other parts of the content is different depending on the intended recipient. This can be as simple as addressing or inserting a name, or as complex as changing major graphical elements to suit an individual. Segmented or customized printing refers to printing for specific marketing demographics. Where variable data printing can be thought of printing for an audience of one, segmented printing is printing for a group of individuals. One of the most common examples of this is direct mail marketing that targets individuals based on past purchases. For example, if someone were purchasing baby diapers and their data were collected, they may receive direct mail marketing that is attuned to people buying things for young children and newborns, like all of the other baby diaper purchasers. And finally, personalized printing is just a special case of variable data printing where the printing is customized to an individual. From the digital printing overview reading, we see a concise analysis of digital printing. Without the need for a plate or other permanent image master, the digital print user saves the cost in the setup time savings. This is a relative advantage to digital printing. In addition, digital printing enables the ability to print small to medium runs in a cost-effective manner. Even runs as short as one copy may be feasible. Furthermore, variable data and print on demand are enabled by digital printing technologies. In Digital Printing and Overview, the author also talks about disruptive technologies, which create a new market and value network, while eventually disrupting an existing market value network, which in turn displaces market leaders and alliances. These disruptive technologies tend to be produced and advanced by outsiders and not incumbents. Although these realizations are not specific to digital printing, there are many players in the digital printing world that were not around before the technology advanced to the point where digital printing technology became feasible. For example, Canon and HP were not in the commercial printing sector at all before digital printing. Canon was known as a manufacturer of film cameras and copiers, and HP was a manufacturer of desktop printers. Because of their digital press offerings, these companies introduced disruptive technologies to the conventional printing marketplace. Other factors noted by Finna in digital printing and overview include the recognition that digital printing often uses frequency modulated screening. You may recall that we distinguish between amplitude modulated, otherwise known as conventional, and frequency modulated, otherwise known as stochastic screening, from a previous class. The author's contention is a generalization. However, most digital printing technologies do not produce a true conventional halftone dot. Most, but not all. Digital printers, especially those using inkjet and dry toners, are almost always using a stochastic screening technology. The construction of the dots is sometimes called dithering to distinguish them from true halftone dots. Other relevant capabilities of digital presses include counterfeit protection. For example, printing with special inks that will only show up under UV light is one capability that is offered by digital presses for counterfeit protected short runs. In most cases, substrates with digital printing are limited versus those that are available for conventional printing. The author indicates that with electrophotography, which is one type of digital printing that will be discussed in a future class, the toner layers are relatively thick. At least that's the case for dry toner electrophotographic printing. These electrophotographic technologies are rather complex, and they use heat to fuse the toner to the substrate. This limits the types of substrates that can be used. Substrate limitations is common for digital printing technologies. Here we have a graph from the Future of Digital Printing to 2018 Smithers-Pyra report that is showing where digital printing jobs are coming from. Now, this study was produced 10 years ago when it was projected to the current year. However, I see no reason to believe that these numbers are inaccurate. So we see that 40% of the digital printing today was previously offset printing, whereas almost 30% of the digital printing is now variable data. 12% is transactional, and 12% is generated via the internet. This is just showing some of the factors that are driving the digital printing market and where it is heading. From that same Smithers-Pyra study, we see that the quantity of jobs that are going to digital printing. And we see that over 45% of the jobs today are 500 or less copies. And over 75% of the jobs that go to digital presses are 1,000 copies or less. Of course, these numbers tail off as the run lengths increase, which is testimony to the economic feasibility models of digital printing technology. You may recall from the beginning of the course, talking about how as run lengths increase, the cost per sheet of conventional printing goes down, where the cost per sheet of digital printing remains relatively static. This realization is borne out from the data shown on this table. From the Smithers-Pyrrha study, there are some interesting comments about the province of various technologies. I really like that term province because the authors are not saying that these technologies are used for these types of work exclusively, but they are saying what technologies particular jobs lend themselves to. In other words, you can always find exceptions. According to the authors, run lengths of less than 250 are the province of digital color printers, whereas 250 to 500 open themselves up to many types of reproduction systems. When you get over 500 to about 10,000, direct-to offset and sheet-fed offset lithography become the technology of choice. Run lengths over 10,000 lend themselves to larger sheet-fed printing processes, whereas the run lengths that go over 50,000, we start to look at web-fed conventional printing technologies. Of course, over 1 million, gravure may come into play, although that is not cited here. The authors also discuss some overlaps that introduce exceptions to these generalizations. For example, look at 40-inch offset lithography. You may recall from a previous class we discussed a 29 by 40-inch offset printing press configuration, which will support an 8-up in position, meaning that 8 letter-sized pieces of paper can be printed at once with a 40-inch press. These compete with so-called half-size presses, which are 26-inch or known as 4-up presses. In the extra large or XL sheet-fed offset lithographic category, which means presses 60 to 80 inches, we see competition with narrow and some wide web applications. This is because the XL presses are printing so many imposed pages with a single impression, the productivity goes up. In the web-fed world, narrow and wide web presses compete, where we also see newer, more automated presses competing with less automated presses. Finally, electronic collation, which is a key feature for many production digital presses, even those that can only print one sheet at a time, may be more cost-effective for very short runs when compared to 4-up printing. So considering these, students are advised to think about the applications and the technology and what's going on in terms of the jobs. Turning to the Buying Large Format article, I really like the author's questions that consumers should ask when considering buying large format printing. Large format printing is typically inkjet. Inkjet technologies are used for signage, billboards, and truck wraps, and things of that nature. But whatever wide format printing is purchased, there are some questions that will help buyers narrow down the best print provider to use for that particular job. These include, is quality or price the primary concern? Does your project have less than 12-point type that must be legible? Will the project be used outdoors or indoors? Will it be exposed to sunlight? Will it be exposed to water? Does it need to be mounted and/or laminated? How will you transfer your prints? Will you use your prints more than once? I like these questions because they help us to think about the end use and how it relates to the technology involved. Some of the information that permeated all of the readings for today rolls up into the genus of digital printing. There are two primary technologies for production-level digital printing. They are electrophotographic, which could be dry toner or liquid toner, and inkjet, which could be drop-on-demand or continuous. Within the drop-on-demand inkjet world, they could be piezoelectric or thermal. The rest of today's lecture will talk about these inkjet technologies. Here we have an illustration from the Digital Printing Overview article where we see analog printing, in this case flexographic printing, on the very left. Electrophotography is pictured next to that, and then the inkjet technologies on the right include piezo and thermal drop on demand, as well as continuous inkjet technologies. We'll be talking about these inkjet technologies today. Again, looking at inkjet, we have two main technologies, drop on demand and continuous. With drop on demand, piezoelectric and thermal are two options. Here we have some illustrations from the Handbook of Print Media. As the name suggests, drop on demand only produces an ink droplet when needed. The two technologies shown here are piezoelectric on the bottom and thermal on the top. Piezoelectric was developed by Epson. Thermal was developed simultaneously by Hewlett-Packard and Canon, but the companies kind of co-licensed them. With continuous inkjet, the drops are produced continually and then divided into two streams. Those droplets that are required for image are directed to the substrate, while those that will not be used in the image are diverted into a gutter and then recycled. Looking more closely at the piezoelectric drop-on-demand inkjet technology, we see that voltage is applied to a piezoelectric material, and that material's length changes when it receives the electrical signal. I like to think of the piezoelectric material as kind of a diaphragm that changes in shape when it receives an electrical current. This piezoelectric diaphragm, some may think of it as a membrane, is called an actuator, and it creates like a miniature eyedropper bulb. The deforming piezoelectric actuator expels a drop of ink from the chamber into the substrate. Piezoelectric inkjet technology is compatible with water-based inkjet inks, solvent-based inkjet inks, and ultraviolet inkjet inks. The other type of on-demand technology is known as thermal inkjet. Inside of a thermal inkjet head, instead of an actuator, there is a fast-acting resistance heater. When voltage is applied to the heater, it boils the ink and creates a gas bubble. The bubble of high-pressure gas propels the ink out of the nozzle. Of course, this limits thermal inkjet technologies to water-based inks. You would not want to use a solvent-based ink when there is heat involved. Working independently in the mid-1990s, Canon and HP introduced versions of thermal inkjet technology. Here we see a diagram showing how the electrical current forms the bubble and the bubble expels the inkjet droplet. This is why Canon marketed their version as bubble jet. When the ink is expelled and the temperature drops, the bubble collapses and ink is drawn into the chamber using capillary action. Here we see a diagram showing the piezoelectric versus the thermal technologies and how they essentially dispel ink from the chamber. With drop-on-demand inkjet, there is an array of nozzles lined up. Here, an approximately 3-inch inkjet head may have 1,000 nozzles. Turning to continuous inkjet technology, it may be helpful to think of this like a garden hose. If you are watering your flowers with a garden hose and you hold the hose steady, a single stream of water comes out. But if you shake the hose, you will see sort of a scatter. It will sort of scatter the water around. This is kind of what continuous inkjet does. It uses a sort of vibration to send continual streams of ink droplets through an electrode, which applies a different electrical charge to those droplets that are required for imaging versus those that are not. Those that are not required for the image are deflected into a gutter where they are subsequently recycled. Here is a table that was provided to me by Professor Eller, showing the different inkjet technologies. We see that drop-on-demand thermal technology uses a compact and inexpensive hardware, but uses expensive supplies and is limited to water-based inks only. We also see drop-on-demand piezoelectric uses compact and inexpensive hardware, but expensive supplies. Piezoelectric can print with a wide range of inks, including solvent-based and ultraviolet-based, as well as water-based inks. Continuous inkjet technology uses a complex and expensive hardware, but the supplies are relatively inexpensive. Continuous inkjet technologies can print with a wide range of inks. And they also have a lot higher droplets per second, more than 6 times higher. This means that you can use continuous inkjet technology for high-speed printing. And here on the final slide, we're showing the next generation of digital press. This particular example is a Kodak Prosper Model 6000. It's a 24.5-inch web press, and it can print at 1,000 feet per minute. Many people believe that this continuous inkjet technology is the most promising technology for unseating conventional printing methods. This prediction has been made for quite a while, but the technologies for both the digital presses, here continuous inkjet presses, and conventional presses are improving. One limitation that you may see as apparent is that the 24.5-inch sheet size cannot do an 8-up imposition, and so therefore it cannot compete productivity-wise with wide web printing and when high volume work is required. However, as the market transitions to shorter and shorter runs, these digital technologies become more and more viable. That concludes our discussion with an overview of digital printing and inkjet printing technologies.